Some results that we get from Livermore are essentially the same. So that we do these kinds of calculations as well. We get a little bit less change in equatorial regions. There's some controversy about how much change will occur in the tropics. If you go back and look at sediment data from ocean cores that are taken aside, you find that temperatures in the tropics haven't really changed very much. And there's some real controversy about whether you'll be able to elevate these temperatures. Our model tends not to do it. The Princeton model tends to do it. But both models get similar results for a global average, and they get polar amplification of the temperature change. If you go out and look at whether this might be happening in the real world, whether you do get polar amplification of temperature changes, this is from a group in England that compared warm years and cold versus cold years. I think it's the 5 warmest and the 5 coldest years during the last century, and looked at the temperature change. Indeed, what you're getting is amplified changes in polar regions. Most of the warming is occurring in high latitudes, and not much is happening in the tropics. Part of this, of course, is going to be due to you have so much ocean in the tropics that sort of buffers the temperature change. But it really does seem to occur in the real world that you're getting an amplification of the temperature change in high latitudes. Another thing to see from this slide is that the changes are not nice zonal changes. It doesn't occur, you don't get the same changes at all longitudes at the same latitude. And so that's something that people, well, that the models are not yet able to really resolve. They're starting to get some ideas of that, but not doing it very well. It makes kind of a difference. And on this one, it's going to be interesting. This is like a lot of warming in the grain belt, especially the Canadian grain belt. And in some places up there, they're actually limited by temperature and how much grain they can grow, and so that will be presumably a benefit to what happens in Canada. Well, not only do we get the agreement with the observation, but I just want to sort of make some comments about there have been quite a few modelers who have made studies. This is only a few of them. If this is the present natural variability of the climate, sort of varying back and forth a little bit around 300 parts per million, if you look at what happens when CO2 doubles or quadruples, most of the modelers are in sort of a band of what's happening. There are a few outliers. And one of the jobs that's going on is to try and explain why they're out there. There's a group at Goddard in New York that has some relatively high values, and in fact actually has some values that are over 4 degrees for how much warming would occur with a doubling. There are a number of people who are projecting very, very little change. One is even a global model. That particular model fixed the ocean temperatures and then ran what happens if you double CO2. That turns out to be an important simplification if you fix ocean temperatures, if you don't allow them to rise. They've since run with a variable sea surface temperature and get a number up around 2, I believe. There are some empirical studies, and we can maybe talk about them afterwards if people have read the articles in, well, this one's been in Science, and that get relatively low numbers. We can talk about those, perhaps in the questions if people are interested. The present National Academy estimate, before you go on here, is basically, we'll go back to that last one for a second. The present National Academy estimate, which just came out in a report, I'll flip it, which came out in a National Academy report in mid-July, is still 3 plus or minus 1.5 degrees for a doubling. Most of the models now are in this range of 1.5 to 3, and so I guess if I were going to make an estimate, I'd sort of put a 2.5 plus or minus 1 or 1.5 as a number. But that doesn't mean that's necessarily the right answer. That's basically where most of the modelers are, and most of the outliers can be explained. Well, let me talk a little about the mechanisms that are leading to this kind of change. The next view graph shows sort of one person's view of where the energy in the atmosphere goes, again in terms of solar units, 100 units coming in and stuff being reflected and going around. The critical issue is the infrared radiation budget, where CO2 has an influence. If you remember from the previous, one of the previous view graphs, what I was saying was that about 1%, 1 unit here is absorbed in the atmosphere due to doubling of CO2, and about a half a unit at the surface. And the question is, why does that lead to a temperature change of 3 degrees? Well, let me just start with half a unit at the surface. The 1 unit in the atmosphere actually gets into the cycle as well, and talk about where that energy is going to go. Well, one thing it might happen is you might warm the surface a little bit and let it be re-radiated to the atmosphere. Well, if you look at what happens to radiation that goes up into the atmosphere from the surface, 89 units are going up and 81 are coming back down. So basically 90% of the energy that you radiate up comes back down, and you have to deal with it again. And the same thing is basically true of clouds. You're radiating up 15 units and getting 12 back, so it's very hard to radiate energy away. You have to go through this. Instead of getting rid of 1 unit, you really have to increase your radiation by 10 units in order to get rid of a net of 1 unit. Well, if you can't do it in radiation, how else can you do it? Well, you get rid of sensible heat, which is basically determined by the difference in temperature between the warm ground and the cooler air. That turns out to be very hard to change. That gradient is very hard to change. It's controlled by sort of the dynamics of the atmosphere and the convective aspect. So it's hard to get rid of an additional unit here, and so you're stuck with having to get rid of it in the evaporation process by increasing the rate of evaporation that goes. Well, where does this energy go? Well, when it goes up, some of it goes into the clouds here and then is radiated away. Well, where does the radiated energy go? Well, some goes up and about an equal amount goes down, but most of it goes into the atmosphere. Where does most of that radiation into the atmosphere go? About 2/3 of it goes down back to the surface, and so you have to deal with it again. The same is true of this. This is sort of energy that comes from the convective overturning of the clouds, and it basically heats the air that is subsiding. That ends up being energy that is in the air, and where does that go? Well, a lot of that goes back down. So basically what you're doing is just recycling the energy. It's sort of like compound interest rates. But you're getting an 80 or 90% return on your money, and it's very hard to get rid of energy from the surface. And these are the processes that are causing the major change. So if the next slide sort of summarizes the factors, the direct effects, the direct radiative effects in the water vapor that occurs because of these direct radiative effects turn out to be a relatively small fraction of the total change that occurs. Most occurs because of this intensified precipitation cycle and transfer of heat up into the atmosphere and then back to the surface. And then some occurs because of ice albedo effects. So that most of it is occurring because of these feedback mechanisms. I perhaps ought to, well, I haven't really said anything here, and maybe I ought to have a little aside to comment on whether one can really believe that the models are working and how one verifies that models are working. It turns out we don't really understand, well, we don't really have any good test cases to test the models against. We understand the seasonal cycle reasonably well and how the temperature warms and cools, but that doesn't really test the long-term mechanisms that we get into when we're dealing with carbon dioxide. Where you're working about what accumulates over 50 or 100 years. You'd like to be able to use the ice ages as a test case, for example, but people don't really understand why that occurred. There's a lot of thoughts, and the prevailing opinion is orbital elements, but there are a lot of complications involved there. So there are not a lot of test cases to assure us that these models are working. And I'll come back later, I guess, to some ideas about looking for evidence of change as evidence that the models might be working. The other thing one learns from models is that not just does the temperature change, but the amount of soil moisture changes, for example, because the amount of precipitation and evaporation changes. And this is again from Manabe's model and sort of a schematic of what happens. This is sort of his schematic continent in this particular model. And what he's getting is a drying out in the 40 to 50 degree latitude band, or 35 to 50 degree latitude band. What's interesting is this turns out to be the grain-growing belt of the United States, which is mainly the major grain-growing belt of the world. And so there is real concern about what this drying out may mean. And what is going on in the modeling now is to try and look at seasonal effects of this and and try and refine really if it's going to be occurring in the proper regions. But if you look at past warm periods, for example, you go back to this hypsothermal, which occurred 5,000 to 7,000 years ago, you find that precipitation really did change. First in the low latitudes, these are maps of Africa, lake levels in Africa in the present and 6,000 years ago, and darker dots here mean higher lake levels. 6,000 years ago, the equatorial regions were considerably wetter, which is something that would be predicted from the CO2 models now. That's kind of interesting. And then if you look on the next view graph shows some information on lake levels in the western United States, where during the last glacial, for example, the lake levels were quite high. During this hypsothermal period, this warm period, they were very low. They got a little bit higher in between. Some of them have gotten quite dry recently, but there's still at least some lakes in some of these cases. So the sense that it will dry out in mid-latitudes and get warmer in the tropics is something that is sort of confirmed by the data as well. Another complication that we have to deal with is other trace species. There's other gases increasing, and you've probably heard about a lot of them. I'm not going to go into it, but they all have climatic effects as well. These are just various increases of these kinds of concentrations. Virtually all of them lead to a warming. And so the CO2 estimates of 2 to 3 degrees may be somewhat low just because we're not including these other kinds of factors. Will Kellogg has tried to integrate all these model results and past climate results to make a projection of what the world will really look like when CO2 doubles perhaps and gets wetter regions and cooler regions. As you can see, you got wetter regions in the tropics, drier regions in the key U.S. grain areas and in some of the Soviet grain areas. But the monsoon strength increases. So these thunderstorms that you get right now out of the monsoon kind of climate may actually, I guess, increase, but your snow in the winter may decrease, I guess.